Okay, the recording has been started. Okay, someone confirm if my screen is visible.
Visible, sir.
Okay then. So let's directly jump into the topic. Again, I will have to complete all the Java by March ending. So I will take extra classes on Saturday and Sunday from next week onwards. So today we are going to see about a data type. It is a very special data type, float data type. So in the previous class, we have understood about the char data type, character data type, and we will see the problems. Before seeing the problems, first today we will try to understand about the float data type. Okay? What do you really mean is float data type. Float data type in Java. Okay, the behavior of the float data type is going to be little different. We will also understand how you can represent the float data in the form of binary system. Okay, first of all, I will give you some points on top of float data type. The first point is the size of the float data type is 4 bytes. Okay? When I say 4 bytes, they are collection of what? Collection of 32 bits. 32 bits. The second valid point is the default value. Default value of float data type is 0.0f. So this is the default value of the float data type, 0.0f. Right? And the third point is it is designed to store up to 6 to 7 fractional values. Store up to 6 to 7 fractional, fractional values. Okay. Now there is another point. We will talk about the range. Before even talking about the range, I want you to understand this. Okay, this point is very important. To represent floating point numbers in computers. For example, if you want to represent any floating point number, okay, let me tell you something. So if I have a floating point literal like 123.567, okay, so I can do what? I can assign, this is a literal, so this is the actual data, which is having what? Which is having both the integer part as well as the fractional part, right? And if I want to represent this in Java, I need to take a variable. Let me take the name of the variable as the var itself, right? And the data type has to be what? Float data type. And if you ask me, this is completely valid. If you ask me, I would say that this is not a valid one. So when it could be completely valid? Only when you suffix the literal, literal with the letter F. It can be capital F or it can be small f. If you take any floating point value and this particular literal has to be suffixed with the letter F. Could be small f or it could be big F. Capital in letters or it can be small in letters. And you need to place a semicolon. So this is the complete representation of complete declaration of the float data type. This is a complete declaration of what? Declaration of the float data type. And also what they are saying is, okay, there is a point that you would come across very often. When you read about the float data types, okay, there is a point, okay, the representation of, or else I can say that to represent. 1 minute. Okay, to represent floating point numbers in computer. Floating point numbers in computers. Okay. The IEEE 754 floating point standard is adopted. What does it really mean? IEEE 754 floating point standard is adopted. Okay, what does it really mean? So we know already that if you want to convert any decimal number, for example, if you have any decimal number like 100, you want to store this as a value in the Java, what you would do, you would take a variable name and you would also take the data type. So data type is what? It can be integer, it can be byte, it can be short, or it can be long. Because all these four data types is good enough to store a value like 100, right? And you do what? You do the conversion. This is a decimal number, and internally this decimal number gets converted to the binary number and will get stored in the registry. Right? And when you try to get access, right, again the binary number will get converted to the equivalent decimal number and it would get displayed in the console, right? So the whole number part or the integer part is completely fine. So if you have any number like with as a fractional values also, how this conversion would happen? That is one question. And also you need to understand something here. Okay, let me give you a literal, like for example, I have a number like 1456.678. So this is a floating point number. I can clearly say that this is a floating point number. And the first, okay, if I ask you the numbers that is before the decimal point, the numbers that is before the decimal point, you call them as what? You call them as what? Integer part. Just remember this. Okay, that is the number that is after the decimal point. Okay, the numbers that is after the decimal point, you call them as what? You call them as what? The fractional part. Fractional part. And the combination of integer part and the fractional part is called as what? Precision. I say the combination of integer part plus the fractional part. Fractional part is called as what? Is called as precision. Sometimes they pronounce it like precision, whatever it is. If I ask you what is the precision of this particular literal, what you would say, you would count the number of integer part and you count the fractional part. Okay, there are almost 4 plus 3 is equal to 7. The precision is 7. And if I ask you what is the precision of 12.35, what would be the answer if I ask the precision? Combination of integer part and the fractional part. How many decimals are there in integer? 2 decimals. How many fractional part are there in how many decimals are there in fractional part? 2. 2 plus 2 is equal to what? 4. 4 is the precision. Precision is what? 4. If I ask you what is the precision for 1567.987, what is the precision? What would be your answer? Come on, everyone.
7.
7 is a precision. Okay, just remove the decimal and count the number of digits. You will get the precision. If I ask you what is the precision of what is the precision? Everyone?
11.
11 is a precision. You just remove this, or else you can do how many digits are there in the integer part? Only 1. How many digits are there in the fractional part? You count, okay? 2, 4, 6, 8, 10. 10 plus 1 equal to 11. 11 is a precision. And also, the fractional part is also called as what? It is also called as the scale. Remember. Scale. When I say scale, it is just equal to number of digits in the fractional part. Just equal to number of digits in the fractional part. If I have to take this as an example, okay, 12.34. If I ask you what is the scale of this particular literal, you would say what? You would say you would count how many digits are there in fractional part. 2 digits. So scale is also what? 2. The scale is also what? 2. Okay, now you give me the answer. What is the precision and what is the scale for this particular piece of number? What is the precision and what is the scale?
8.4.
8.4. 8 is a precision. Okay, combination of integer part and the fractional part is going to give you what? 8. Precision. Okay. And scale is what? Scale is what? Because scale is just equal to number of digits in the fractional part, which is what? 4. scalar fractional part. Fractional. Now I have just told you that there is something called IEEE 754 floating point standard. What does it really mean? Let me remove all this. So these are the you should get acquainted with these terminologies, especially the integer part, fractional part, and what is precision and what is a scale. Having said this, let us understand what is this IEEE 754. The acronym for IEEE. The acronym for IEEE is what? Institute of Electrical and Electronics Engineers. Okay, and 754 is just a what? It is just a standard of number published by IEEE. The standard published by IEEE. Okay. What does this institute says? So in order to store a floating point number, if you want to convert a floating point number, if you want to convert a what? If you want to convert a floating point number to the binary representation. Okay, they have adopted a standard. Called the IEEE standard, IEEE 754 standard. Okay, by using the standard, they started storing the binary form of the floating point value by using the standard, IEEE standard. Now we should understand what does the IEEE actually means. Binary number. To understand this, let me give you a small example. Now focus here. Okay. Now before understanding this, let me write a small piece of code. Let me open my notepad. Class A. Okay, in this class, I want to store a value float A equal to something like 123.67. System.out.println. If they run this class, okay, the compilation will not be successful because we should take the main method, right? Public static void main string array box. So we have taken a main method and we have taken a class. So let us run this. First, before running this, let me save this. Okay. A.java. If I run this, what would be the output? Anyone? Can anyone tell me what would be the output?
Same number, 1234.67.
No. The output would be error because I said no. If you are representing a floating point number, you should suffix that with the letter F. Do you remember? I've just said this. Okay, let me run this. Java C space a.java. I'm sorry. C space a.java. Okay, my mistake. Java C space a.java. Okay, see, it says incompatible types, possibly lossy conversion from double to float. It is not accepting because it is not suffixed with when you do not suffix a floating point number with the letter F, this will be treated as what? This will be treated as double by default. By default, this is going to be treated as double. How you would convey this message to the compiler saying that this is not a double value, this is a float value, this is a floating point literal. How one could convey this to the compiler? Just by adding the suffix F. The moment you do this, now it will be like answer is as you have said. There will be no issues with the compilation and there will be no issues with the execution. Java space A. So now there are no issues. Compilation is successful and execution is successful. Let me take a small number 263.3. 60.3. Now if you Java says Java C space Java, Java C space A. If you take the capital letter F, will that give us any error? Java C space Java, Java space A. Okay. Now you see, now let me trace this. Okay, let us trace this. What would happen behind the scenes? Let us trace this. What would happen behind the scenes? Okay, this is our piece of code. In a focus here, this is a piece of code. Okay, and we know there are there is a compiler and there is a JVM. Okay, to activate the compiler, the command is what? The command is java c space a.java. Java c space a.java. Compiler gets activated. Okay, as soon as the compiler is activated, okay, and before that, the name of the source file is a.java. Right? You are saying that please compile a.java. You are saying this to compiler. Okay, the compiler will take a.java and it will perform the compilation. If it is error free, okay, and a dot class file will be generated, a dot class file. And again, you want to execute this. To execute this, you will bring in the JVM. For the execution, the command is java space a. Okay, the JVM will load the a dot class file. While a dot class file, you are clearly specifying it as a. A dot class file will be loaded inside the JVM. Right. So this is the compiler. Don't think I am repeating this. So this knowledge is really important to understand the control, compiler and the JVM. Okay, and JVM will create a main thread. Main thread will get access to the main method. Okay, a main thread will be created by the JVM. It will get access to what? It will get access to the main method. So where is the main method? This is the main method. What is the first instruction? First instruction is very straightforward. Okay, now, but here JVM finds the literal as what? The literal is a floating point literal. Okay, it has to store this value inside the RAM by converting this number, by converting this floating point number into a binary number. But it has a fractional part as well. To do the conversion by considering the fractional part, it will adopt a IEEE standard. We are understanding what is IEEE standard. So this is the value 263.3. If I ask you, this value can be divided into two parts. One is what? One is the integer part, and second one is what? Second one is the fractional part. Okay, first step number 1. Okay. Find the binary number for the integer part. Find the binary number for the integer part. How you would do? We know these things already. We are expert in this, right? So the binary number is what? Binary number is 263. Focus here, guys. 263. 263 is the decimal number, integer number. Okay, this one, integer part, and this has to get converted to the binary number. Okay, 263. Keep dividing this number by 2. Okay, you get what? 131. Balance 1, right? Keep it dividing. Keep dividing it until you get the remainder as 1. 2 6 times, 2 5 times, balance 1. Okay, 2 3 times, 2 2 times, balance 1. Okay, 2 1 times, 6 times, balance 0. Okay, focus here. 2 8 times, balance 0. 2 4 times, balance 0. 2 2 times, balance 0, and 2 1 times. Okay, balance 0. Okay, collect the numbers from bottom to top. So this is how you collect the numbers, right? So what is the equivalent binary number for the integer part, which is 263? Okay, when you ask me, I would say 100. So we are counting it from bottom to top, right? So 100, 000, 100, 100, 000, 111. Okay, and again, so we have just calculated the equivalent binary number for the integer part, and if you see, there is a fractional part as well, right? There is also a fractional part. What is a fractional part? You have 0.3. Okay, to find the equivalent binary number for the fractional part, this is step 2. Okay, step 2. Step 2. You have to, or else I can say that, find the binary number for the fractional part. Okay. So to find the binary number for the fractional part, if it is an integer part, you keep dividing it by 2. When it comes to integer, you do what? You just keep dividing it by 2. But when it comes to the fractional part, you just multiply it by 2. That is the only difference. Because you are trying to find for the fractional part. Fractional means multiplied by 2. Integer means divided by 2. Fractional means keep multiplying it by 2. When you do this 0.3 into 2, you get what? 0.6. Now focus here. Focus here. You have to collect what? You have to collect the integer part. You get an answer. After getting the answer, you have to collect only the integer part, which is what? 0 here. Should we stop here? No, we have to continue. We have to continue multiplying it by 2. Until when? That we'll understand. Again 0.6. 0. So take this value 0.6. Okay. Into. Instead of doing this, just imagine to take only 0.6. 0.6. Okay. You don't consider the integer part. You take just 0.6 and the 0.6 is nothing but 0.6 into 2. Okay. Which is going to give us what? Which is going to give us 1.2. 1.2, right? 1.2. Okay. Please ensure that you are collecting the integer part. This value, collect it. Okay. And again, take this number 0.2. 0.2. Okay. 0.2 is nothing but 0.2 into 2 again. You will get what? You will get 0.4. Okay. Collect the integral part number, which is what? 0. Okay. Again, take this 0.4. 0.4 is nothing but 0.4. Okay. Into 2. You get what? You get what? 0.8. Okay. What is the answer? Collect the integer part, which is 0. Okay. And again, take this 0.8. 0.8 means always it has to be 0 into 2. Okay. You will get what? You will get 1.6. Okay. Is equal to what? You will collect this one. Okay. And again take 0.6. Okay. Into 2. You will get what? You will get 1.2. Okay. You will collect what? You will collect 1. If you observe one thing here, we are going to get a pattern. See, this is similar to this line. If I keep doing this over and over again, don't you think that these steps will be repeated once again? Yes or no? Because this is just exactly similar to this line. Even though if I keep doing this, if I follow the same steps, I will be getting the same answers. These answers are repetitive. Okay, you get 0, 0, 1, 1. Right? You keep getting what? You keep getting the same value. Okay, this step will get back to you here. Yes or no? What would be the answers you will get? 0, 0, 1, 1. So these values are repetitive over and over again. 0, 0, 1, 1. So I can conclude here. The moment you find this pattern, you can stop performing this. Okay, now what is the fractional part that we have? We will take the fractional part from top to bottom. You will collect all the numbers from top to bottom. Okay, which is what? 0, 1, 0, 0, 1, 1. Okay. 0, 1, 0, 0, 1, 1. Okay, and 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1, 1. And it keeps going 0, 0, 1, 1. It is going to be just like that. Okay, it will be going infinitely. Okay, this is the fractional part. So this is what? This is symbolically representing what? This number is representing the fractional part. Fractional part. Okay, now we are able to find the equivalent binary number for the integer part as well as the fractional part. For the integer part, what is the binary? What is the exact binary number? This one. 1 0 0 0 0 0 0 1 1 dot. Okay, I can bring it like this. Okay. So this is just equal to what? 263.3, right? 263.3. Okay. The integer part is here and the fractional part is here. Okay, after this, should we stop? No, we should not stop. We should do 3 more things. We should do 3 more operations. This is going to be very easy only. Just stay focused. Okay, firstly, we have done the conversion. We have converted the integer part to the equivalent binary number. We have converted the fractional part to the equivalent binary number, right? And we are going to do few more steps. The next step is like this, guys. The next step is like, need to convert this whole thing into the scientific notation. When I say how to convert a number to a scientific notation, let us say that I have a decimal number like 7,900. I have a decimal number like this. If I want to convert this number to a scientific notation, okay, so let us say that I have a number like 7,900.153. I want to convert this to a scientific notation. So this is a decimal number. Okay, this number is equal to 10 to the power of 0. If I multiply it by 10 to the power of 0, the result is not getting affected. Both are same. This number is same as what this number. The result is not get affected. If you want to convert this to the scientific notation, just take this decimal point. You just move this decimal point towards its left. The decimal point is here now. You just move it towards the left to one place value. Okay, you will increase the power to what? You will increase the power to 1. Okay, if you move this to two place values, you will just increase the power to what? You will just increase the power to 1 becomes 2. If you move this to 3 decimal values, 3 places towards its left, the power will be increased to 3. Okay, if you just move this, okay, from here, if you are moving this here, you keep increase the power to 1. Instead of here, if you want to move this here, you will keep the increase the power to 2. So the decimal conversion is what? I mean, the scientific notation is what? Okay, 7.900,153 into 10 to the power of 3. This number is same as this number, but you are representing this number in the form of scientific notation. Scientific notation. Likewise, when you want to represent the binary number in the form of scientific notation. Okay, now this is for an example. I have taken this as an example. You are taking the decimal number to get represented in the scientific notation, but when you want to represent the binary number in the form of scientific notation, you do the same thing. So the point is here, right? The actual point is here. We want to shift this point to 1, 2, 3, 4, 5, 6, 7, 8. 8 places. 8th place. This is the 8th place. Okay, how the resultant value is going to be 1.0000011, okay, 01, 0011, 0011, and remaining things is going to be what? 0011, 0011, 0011, and so on. Okay, and so on into 2 to the power of 8. Because I am shifting to 8 places. This point is getting shifted to 8 places. That's why into 2 to the power of 8. Why 2 to the power of 8? Because this is a binary number. Okay, when you want to convert a binary number to the equivalent scientific notation, you should increase it by 2 power. 8 is the shifting places. So we have got the equivalent scientific notation. Okay, this number has converted to scientific notation. Okay, now the real magic is here. Okay, so this is what the float data type is of how many bits? 32 bits, combination of 4 bytes, collection of 4 bytes. Okay, 32 bits, right? So I want to take 32 bits here. Let me take it really quick. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 16, 32 bits. Now focus here, guys. So this is representing the 32-bit registry. Why 32-bit register A? Because the size of the float data type is of how many bytes? 4 bytes. 4 bytes is the collection of what? 32 bits. That's why 32 bits. Okay, the first bit. Okay, the first bit, focus here. The first bit, it is resigned for what? It is reserved for the signature. It is reserved for the sign. So what is the number that we are dealing with at the moment? So we are dealing with the floating point number, which is 263.3. So this is the positive number. Okay, so the first bit is always reserved for the signature. The first bit is always reserved for what? Reserved for the signature. Oh, let me do it like this. Okay, this bit is reserved for signature. The next 8 bits, when I say next 8 bits, okay, 1, 2, 3, 4, 5, 6, 7, 8. This next 8 bits is reserved for what? Is reserved for the exponent value. You got one exponent value right here, 2 to the power of 8. 2 to the power of 8. So this 8 has to be reserved here. The exponent value has to be reserved here. And the remaining how many bits? Remaining how many bits will be there? 23 bits now. Remaining 23 bits is reserved for what? Is reserved for this complete values that we have got here. Okay, now focus here. I want to take these two numbers. Now you see. Okay, so the first, this is reserved for what? This is reserved for the signature, MSB. Most significant bit will tell if your number is a positive number or a negative number. If a number is a positive number, just put the 0 bit here. This is done. Okay, and this 8 bits are reserved for what? Reserved for the exponent value. The value of exponent is what? 8. And again, when you want to store 8, please remember one thing. So you have 2 to the power of 8 here, right? Okay. This power can be either, sometimes it can be a positive number. In our case, it is a positive number. Sometimes it can also be a negative number. Okay. What the IEEE pattern says, what the IEEE says, if you want to represent both positive and the negative number, you need to use a concept called the bias concept. When I say bias, it is something like you don't reserve this. Okay, you don't reserve this MSB for either positive number or 0 or 1. If it is 0, you may say that it is a positive number. If it is 1, you may say that it is a negative number. But when you take the bias concept, you need to worry about reserve this place. You don't have to worry about reserve this place. Instead of reserving that place, you should use a bias concept which has the value of 127. If you feel that the number is positive number, you would just add the 127 with the value that you have, which is 8. This is going to give you 135. In some cases, you may be dealing with the exponent value which is of something like -6. If you have this, take the bias number which is 127 and subtract it by -6. You will get some number which is what? 121. Okay. If it is a positive number, add 127 with that positive number. If the exponent value is a negative number, remove that 127 negative number by 127. This concept is called as what? Biasing. What is an advantage? You do not have to reserve a separate bit for the MSB. If you raise the powers, okay, 0 to 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, 2 to the power of 5, 2 to the power of 6. You calculate all the powers, you will get 127. And there is one additional bit is also reserved. Additional bit is also there. If you're not reserving that for negative number or for the positive number, what you can do, you can, this is talking about the bias concept. Whatever the exponent value that you're getting, which add that with this number, you will get a big number. Store that number as it is. Okay, if the exponent value is a negative number, remove that number from 127. You will get one number 121. Convert this to the binary and store it here, so that you do not have to specifically reserve the signature here. Okay, so in our case we have what? We have the number like 2 to the power of 8. Okay, 2 to the power of 8. Okay, 127 plus 8 is going to be 135. Find the equivalent binary number for the 135. 135. Keep dividing it by 2. 2 6 times, 2 7 times, right? And you get 1. And again 2 3 times, 2 3 times, and you get 1. Again 2 1 times, 2 6 times, you get 1. 2 8 times, you get 0. 2 4 times, you get 0. 2 2 times, you get 0. And last 2 1 time, you get 0. So collect the numbers from bottom to top, which is what? 1 0 0 0 0 triple 1. Right? So this number, this equivalent number can be stored here. 1 0 0 0 0 triple 1. Okay, this is what? This is exponent value. You are you are storing the exponent value here. Okay, and the remaining values are there, no? What are the remaining values you have? Okay, after storing the exponent value, you have the remaining numbers, right? Okay, that will be stored here. Okay, what are the remaining numbers? This fractional part. Till the fractional part. Okay, if I have to store that numbers here, what is the fractional part? 0 0 0 0 0. Okay, 1 1 1 0 1 0 0 1 1 0 0 1 1 0 0 1 1 0. It can accommodate only to a certain number. Till that, you will fill the numbers that you have with you. You will fill the numbers that you have with you. So remaining numbers will be rounded off. Rounded off. Okay, this pattern, these steps that we have followed just now is called as what? IEEE steps. So when I say the floating data point has adopted IEEE 754 to store the floating point values, this is what it means. If you observe it completely, we have just we have completed this only with the 3 steps. Okay, for any given number, if I say 45.45, okay, we will do this example also. If I say 45.45, take the integer part 45, take the fractional part 45, divide the integer part by 2, okay, to find the equivalent binary number, and divide and multiply the fractional part into 2, 0.45 into 2. The fractional part you keep multiplying it by 2, and the integer part you keep dividing it by 2. So you will get some numbers here, and you will also get some binary numbers here. After this, okay, you will get some numbers now. You will convert that to the equivalent scientific notation. Scientific notation. After the conversion, okay, the number could be something like, okay, it will be zeros and ones into 2 to the power of some number. Let us say that you have a number like 8, not 8. Let us say you have a number like 5, 2 to the power of 5. Okay, and create a 32-bit registry. We'll be creating a 32-bit registry. Instead of doing that, okay, the first bit is going to be what? Is going to be MSB, which is called as what? If the number is positive number, you will replace the MSB with 0. The next 8 bits is reserved for what? Reserved for the exponent. You have the exponent 5, right? This 5 has to be added with the bias, which is 127. Okay, the resultant value is going to be what? 132. Okay. You will find the equivalent binary number and you will store it here for the exponent value. What the remaining numbers? Remaining 23 numbers will be there. Okay, you will consider the fractional part of the 23 numbers. That's it. This standard is called as what? This standard is called as what? IEEE standard. Even in Java, even in Python, in order to run this application, if you want to execute the piece of code which I have taken as an example, internally it will go through the IEEE steps to store the value into the data type. That's why they call it as what? IEEE standard. You want me to do you want me to help you with another example? Can we go with another example? Yes or no? Everyone? Can we do another example? Shall we take any simple example? Come on.
Yes, sir.
We will see another example. Huh? Now focus here. If you are not understanding the first example, I will keep the next example very simple. Focus here. Okay. So let us take the number as 45.45. Focus here, guys. 45.545. You have a number like this, you can say that it is a floating point number. First take the integer part, which is 45 itself. Okay. Keep dividing this number by 2. Okay. 2 2s are 4, 2 2s are 4, and you get 1. 2 1s are 2, 2 1s are 2, you will get 0. And 2 5s 10, you get 1. 2 2s 4, you get 1. 2 1s 2, you get 0. Right? You collect the numbers, you collect the reminders from bottom to top. What are the numbers that we have? 1 0 1 1 0 1. Okay. You have successfully found the equivalent binary number for the integer part. Now calculate the equivalent binary number for the decimal part, which is 45. I can say that 0.45. Okay. If it is a fractional part, you need to keep multiplying it by 2. For integer part, divide by 2. For fractional part, multiply it by 2. After the multiplication, what you will get? 0.45 into 2 equal to 0.90. Okay, 0.9 I am saying. Okay, collect this integer part and keep it here. Okay, and take only the fractional part for the next multiplication. 0.9 into 2. So 0.9 is nothing. 0.9 is nothing but 0.9 into 2, which is going to give what? 1.8. Collect only the integer part and keep it here. Consider the fractional part for the next set of multiplication, 0.8. Again multiply it by 2. Okay, you get what? You get 1.6. Okay, collect the integer part and place it here. Take the fractional part, which is 0.6, and multiply it by 2. Okay, and you get what? 1.2. Okay, collect the integer part 1. Take the fractional part for the next multiplication, 0.2 into 2. You get what? You get 0.4. Okay, and what is a fraction? What is integer part? 0. Okay, take the fractional part and multiply it by 2. 0.4 into 2. What is the value that you will get? Okay, 0.8. Right? And you will get the remainder as 0. Okay, and again what? 0.8 into 2. Okay, you will get what? 1.6. Okay, you have to collect what? 1. And if you focus here, okay, this step is similar to this step, right? No matter what I do, okay, this is again repetitive. Okay, after this I will get 1 0 0 1, and again 1 0 0 1 will be repeated. Don't you think so? Okay, I am able to find the, so okay, this time you have to collect all these numbers from top to bottom. Okay, how do we collect? We have 1 1 1. We are missing one more one, right? Okay, we have 0 also. Okay. 0 1 1 1, 0 1 1 1 0 0 1. Okay, 0 1 1 0 1. Okay, again from this one it is repetitive. 1 0 0 1. One 0 1, again repetitive, no? So 1 0 1, and again 1 0 1. It keeps going like that. Okay, so this is the fractional part. Okay, just use a decimal dot here. And what is the equivalent binary number for the integer part? 1 0 1 1 0 1. 1 0 1 1 0 1. Okay, you have the integer part as well as you have the fractional part. What you have to do after getting the integer part and the fractional part, you need to do what? You need to convert this to the scientific notation. What is the scientific notation? Okay, what is the scientific notation? You just shift this decimal point towards the left side. Okay, towards left side. For how many places? 1, 2, 3, 4, 5. When you are shifting it for 5 places, you need to multiply it by what? 2 into 10 to the power of 5. 2 to the power of 5. 2 to the power of 5. What 2 to the power of 5? All these values into 2 to the power of 5. So I can rewrite it like 1.01101 0111 001 1001 1001 1001 1001 and so on. Keeps going. Okay. So now it is completely in scientific notation. After getting this in scientific notation, what I said, how many bits we have for the float data type? We have 32 bits. So first bit is reserved for what? Signature. What was the number that we have taken? 45.45. 45.45 is a positive number, right? So the first bit is reserved with the value 0. What are the next 8 bits? Exponent value. What is exponent value? 5. Okay. 5 is a positive number, right? If it is a positive number, you need to add this number with the bias, which is what? 127. What you would be getting? You would be getting what? 132. Okay. You convert this to equivalent binary number and you will place it here. What is equivalent binary number for 132? Let us calculate that also. 132 divided by 2. So 6 times 12 to 6 times 12 0 to 33 times 0 to 16 times 1 to 8 times 0 to 4 times 0 to 2 times 0 and at last to 1 time 0. So what is the values that we get for the equivalent 32? 1 0 0 0 0 1 4 zeros, right? 1 00. So this is the equivalent binary number for the exponent value. We got this is an equivalent binary number for the exponent value. Okay, 1 4 zeros, 1 00. Okay. So in the place of the exponent value, you add 1 4 zeros, 1 3 zeros. The MSB is completed. The exponent part is also completed. Okay, the remaining, there will be how many bits here left over? 23 bits are left over, right? Because out of 32, 1 has been assigned to MSB and the remaining 8 has been for the exponent. So remaining 23 will be there, right? So the 23 bits. For all the 23 bits, you start writing the number from here. After the decimal from here, and you keep writing, keep filling the numbers, how much you get. Okay, and what about the number that is not yet filled? That will be rounded off. That will be rounded off as the fractional part. Okay, so the answer is going to be what? 0 1 1 0 1 0 1 1 1 0 0 1 1 0 0 1 1 0 0 1 1 0 0. Okay, so this is how it gets stored in the memory. Okay, take first 4 values to keep it simple. 0 1 0 0. I'm taking it like this, 4 bits. I'm separating it according to the 4 bits. 0 0 1 0. Okay, and 0 0 1 1. 0 0 1 0. 0 0 1 1. 0 1 0 1. Okay. You can separate it until you get 34 bits. This is how it gets stored internally. Making sense? You want to see another example? You just write these 2 examples. You just try to understand these 2 examples. Okay? It is just like no one is going to ask this in the interview room. This is just to understand what is the IEEE standard. What does it mean to say IEEE standard means? So these many conversions will happen internally. So this conversion is called as what? IEEE standards. Okay, in the interview room, you would be answering a floating data type is adopted a concept called IEEE 754 standard to store the floating point number into the equivalent binary number. So this is what it is actually. You do all these steps. Internally, these steps will be done by the computer to ensure that the right value is getting stored in the registry.